What we want to look at now is how to describe a complex number in a different form that makes it a little bit easier to use on the Argand diagram. And what we're going to do is we're going to put in what we call a modulus and argument form. Basically what we want to do is describe the distance of the point, the complex number, on the point from the origin, from 0 plus 0i. Basically we want to describe it, how far away it is from it, and at what angle, from 0 to 360 or whatever. We're going to deal basically minus 180 to 180. So the idea here is if we have a look at our point here, x plus iy, and we draw up a right angled triangle. So looking at that, if that's a distance r, it could be any variable, but that would be x across and y up. So it's going to be a right angled triangle there. So if we want to do that, what we want to do is describe x in terms of r and theta and y in terms of r and theta. It's what we're going to call basically a parametric equation. R is going to be a set value, but we want to, instead of two variables, we're going to have in terms of one variable theta. Now we've done that before because we've looked at the idea, or when we've got something like that, if r was 1, say, we'd have x squared plus y squared equal 1, or cos theta, and we get the cos squared theta plus sine squared theta is equal to 1. We get that result. So it's the same idea here. So basically what we want to do is split into two parts. Now the modulus, which is going to be the distance r. So we describe it as z with a little bars around it, a bit like the absolute value as such there. It's described by taking Pythagoras' theorem on this. So r would be the square root of x squared plus y squared. So the modulus there is the distance. No, and we're going to take a distance every time, so it's going to be positive. So that's why it's taking the idea of an absolute value as such, because it's going to be a positive distance no matter which direction we go in. Like no matter where the point is, the distance to that point would be the same. So we get this modulus of z being the square root of x squared plus y squared from that triangle. What we should note at the moment as well is that the idea that a modulus of z all squared is the same as the modulus times z times its conjugate, because if you remember, x plus iy times x minus iy was x squared plus y squared. So the modulus squared is going to give you the same as multiplying the complex number by its conjugate. So just a little thing to pay attention to. Also, the argument. The other part is the angle that it's at. Now, if it's between 0 and 90 here, obviously it's going to be given a different angle and being at different values if it's somewhere else. So what you've got to do is pay attention to the quadrant that you're in. So here I'm going to get my argument of z to be y on x, inverse tan of y on x, because I take tan of theta and it gives me y on x. Remember, I've got x and y, so they're the values that I can play with. So the idea is to have a look at y and x there and say, well, I know one of my ratios would be the opposite on the adjacent, so y and x, so I get tan of theta is equal to y and x, or theta is equal to inverse tan of y and x. Now that's going to give me the acute angle in that triangle every time. So if my triangle's over here, remember it's in the second quadrant, I'm going to subtract that angle from 180 to get my required argument, because even if my if my point is over here, it's going to be described by that angle, because it's how far away it's going from the positive real axis. If my point was down here, we'd be saying, well, how far it is around to there, or we could look at it, well, how far is it around to there? So we get our angle theta there and subtract it from 180 as such there to get that angle there if we're working in the third quadrant or fourth quadrant. So keep that in mind when you're doing it. We've got to pay attention to the quadrant. So what we can do then is describe the theta here as r cos theta. Oh, sorry, the distance here x is r cos theta, and y would be r sin theta in that regard as well. So what will we do? We've got our angle theta. We can put it in there, and then so our point there, x plus iy, would be equal to r cos theta. So we get it to right. R cos theta plus I r sin theta. And you could start to put it in that form then. So factorize your r out, and say, well, r cos theta plus I sine theta, and then we could write it in what we call our cis form. Basically, this is just a shorthand way of writing the complex number in modulus argument form. R cis theta is basically saying this, it's cos theta plus I sine theta, but if you want to write it like that, it's just a shorthand way. So that's what modulus argument form would look like. Now, just a note on the angle. We can really write our angle in whatever form we like. If that's theta, and if we add on 360 to it, we get the same angle, and it's going to be the same as what it would be as an acute angle as such there. What we generally take is our domain for theta. So how we generally tend to write theta is somewhere between minus pi or minus 180 and 180. So instead of our normal 0 to 2 pi or 0 to 360 that we start here, we usually look at starting in the third quadrant there and going around that way from minus 180 to 180. So that would be, and it's equal less than, it's not going to be equal to minus pi, but if it's on the axis here, we're going to take pi. Now, that's only if what we want to take called the principal argument. Now, we can take really any number. So the idea that the argument of z could be any general solution there, no matter which way we're going, positive or negative, then you could look at that. But realize that if you do ask for the principal argument, generally put in the principal argument, we bring it back to somewhere between minus 180 and 180. That's the general convention, and that's where the principal argument is. So as opposed to the 0 to 2 pi, which we've generally dealt with in previous courses in 2 unit and 3 unit, and looking at angles, and in the 4 quadrants we go between 0 and 2 pi for 1 revolution. For complex numbers, we're going to deal with a principal argument that's going to be between minus 180 and 180, or minus pi and pi. So that's where our angle's going to be. Again, if it's not asking for a principal argument, you could write whatever angle there, as long as that would be an equivalent there. So theta plus how many lots of 2 pi you want there.